Okay, hello everyone. I'm recording and I've got these notes for you on systems of equations. Systems of equations may look a little familiar, but we're going to dive into some of the conceptual aspects of them today to make sure we understand what we're talking about mathematically with features of the graphs and the equations when we have systems of linear equations today. So let's define a few terms. I'm going to move quickly through all of this. At some point, you might want to stop the video to build the graph that I have up on the screen, but I have two examples typed out in Desmos, one out in a TI-84, and I'm going to try to juggle all this technology while I make this video and see how it goes. So a system is just two or more linear equations, and if it's linear equations, it's a linear system. And a solution is a value or a set of values that make all of the equations in the system true. So I have this just kind of picking this apart in example one. Here's a system. This is a system of linear equations right here. By the way, I'm going to stop right now and get this in a more familiar form. I'm going to call this y1. In general, I'll do this. The first equation I'll call y1. And if I add 3x to both sides, you can see I can get this in slope-intercept form pretty quickly. So I'll actually write this as y1. Or y1, if I divide both sides by 2, is 3 over 2x plus 4. And there we go. I may not color code all of these, but here for starters, let's say this is y2. And I'll do the same thing if I try to get y2 by itself. Subtract x from both sides, divide both sides by 2. And I have a line in slope-intercept form with a slope of negative 1/2 x and negative 4 there for minus b. So you can graph these by hand. I gave you a little graph here, but I'm going to pull this up in Desmos. I actually typed both of these out in Desmos right here. Notice Desmos has this nice feature. I can actually type both of these in standard form. You see I have x and y on both sides. This is my y1 right here, my first line in red, and same thing here. This is my y2. So I solved for them in slope-intercept form to get y by itself, so you could see how you could graph these by hand, but also this is a nice feature in Desmos where I just have them plotted up. So I'm going to graph them. I've got here about 1, 2, 3, 4 points on this graph that I will sketch by hand just to get these up. If I keep my y1 in purple, let's see, we're up here. The y-intercept is actually somewhere up here. I didn't have that on this graph, but don't get thrown off by that. But once you get a point on there, I'm going down up 3 over 2 or down 3 left 2 would be fine. Down 3 left 2, and this is my y1. And let's get y2 up here. It's got a y-intercept down here, down 1 over 2 or up 1 left 2, and there we have a point where they coincide, which is good because this is our solution right there. So you can see it graphically, a point where the lines intersect will be a solution to the equation. And there's two things I want to hit as to why that will be a solution to the equation. Here I wrote both of those lines, 3 over 2x plus 4, negative 1 over 2x minus 4 are both our lines, y1 and y2, and I just input some x values here that I have in the table. These are the x values in the table that we're going to fill out. These are the various values, and notice right here at x equals negative 4 is where I have an output value of negative 2 and negative 2 here on the graph. So I built this table in Desmos, and you could do that. You could pause the video and do that yourself or do it in your TI-84. But here are the values. I don't really care too much about all these values. Here are the output values of both these equations for these x values. But what I care about is where we get right here. At an x value of negative 4, the y outputs for both of these are negative 2 and negative 2. Again, I'll record the rest of these values, but I don't really care about anything else that's going on this table. And that coincides to this solution point, which is negative 4 negative 2 right here. So we've solved the system graphically, and I'm going to do one last thing where if I take that point, that solution point, negative 4, negative 2, and for y1, maybe I do a quick check up here. For y1, if I plug the x value in and then plug the y value in, this should make the equation true. This does give negative 12, positive 12 rather, minus 4 is equal to 8, and that is 12 minus 4 is 8, so that's true. And I can do the same thing with my blue y1 equation. If I plug those values in, negative 4 for x plus 2, negative 2 is equal to negative 8. I just took the equation here and wrote it out. That will give me negative 8 is equal to negative 8. So that one point with that x value and that y value makes both equations true. All right, so this one example, like I said, kind of packs everything in together. There's a couple more that we can do quickly. The growth rates from the birth of two different species of shark are given by the following equations. At what age will the two species be the same length? Use a TI-84 or Desmos to find your solution. All right, so here are the two equations. So this is for a Greenland shark and a spiny dogfish shark. I have no idea what those species are, but this is modeling length in centimeters, the length of the fish as a function of its age in years. Before thinking too much about these equations, I just took both of these, and once again, you could do this in your calculator or in Desmos on this other tab. Here are both of these equations. You can see here's y1, the first one. As age increases, it's got a certain length at birth, and as age increases, it gets longer. But this blue shark here, the spiny dogfish, starts at a smaller length but grows faster. And at what age are they the same length? I'm solving this system of equation, same output value. Here's the point of intersection. At an age of 20 years, they'll have this output value, this length of 52 centimeters. And so I'm just going to write for my solution. You're welcome to use your graphing calculator or Desmos to solve a problem like this. In fact, that was in the instructions. I'm just going to write, so the point of intersection, or rather, they have the same output, in this case the same length, is at x is equal to 20 and y, I believe it was 52. So the answer is they will have the same length at 20 years old. All right. So this point of intersection, by the way, you can see on Desmos that I just clicked this point of intersection, but I'll show you how to do that in the TI-84 in the next example. And this is where I might rely on you all to input a table into Desmos or use your stat edit lists, because we are going to take all this data. In example 3, it says the following table shows New York City and Los Angeles populations from census data from 1950 to 2000. Using linear regression models, predict when the two cities will have the same population. I'm going to take both of these and I'm going to do two linear regressions. Let me show you how I did this in the calculator. I'm going to have 3 lists set up. This is my final result. Stat, edit. Here are all of my lists. I took 50 as 1950. However, it doesn't matter what you choose in your X columns because I'm using the same X values for both lists. But if you want to copy me, I have 1950, 1960, 1970. And over here, you can see you're only seeing 3 digits of precision in this L2 list entry. It says 1.2 E7. That's 1.29 times 10 to the 7. It's written in scientific notation. But you can see down here, this is the 12,911,994 people, that population number that I got from this first entry for New York City. In this case, New York City is my L1, and Los Angeles is my L2. So I input all of these values, and this is where I kind of have to hurry things along, but I'm going to put a note in the video. You can stop here if you want to sit for a moment and copy my lists. Put your New York values here in L2, put your L3 values here in, put your Los Angeles values here in L3. I'm going to put up on the screen for a second what I chose as my window. I then turn my stat plots on. I have L1 and L2 in blue, and L1 and L3. So these are the same X values, but I'm taking my New York numbers as my Y values and my Los Angeles numbers as my Y values for plot 2. You can see the points in blue and red, and then I do stat, calc, linreg. And to get our Y1 for our New York numbers, I will make sure my X list is L1, and this is where we will change our Y list to L2 and go down and hit calculate. Just like we've done before, I'm going to record these values. Here's my slope and my y-intercept. I have all this kind of written down and ready to go. So again, this is supposed to be, this is my L2 list and this is my L3 values, rather. These are my L1. Sorry about that. But if New York City is Y1 and Los Angeles is Y2, I'll have my New York City equation as I'm rounding to the nearest integer. That's what, something like 146,000x plus this 5.5 million number. That's all right. We don't need to understand the meaning of these numbers yet. We're just writing down the equations. And then, as I've got it set up with L1 and L2 here, I can do stat, calc, and I can run another linear regression. With L1, keep your x values the same, but now I'm going to move this, if you're doing this with me, to L3. And that's going to calculate a linear regression for the same x values, but with the Los Angeles numbers in my L3 instead. And I'm representing that as Y2. Sorry, I already have that written down. So these, I'm just double checking my numbers, are both correct. I now, in order to plot all these in this window, I already typed these out in my y equals. I have y1 and y2 as I have written on the notes. And this is how I have made my graph. On Desmos, if you did this yourself, you can click that for the point of intersection. On your calculator, do second calc and go down to intersect, like we did one other time in class. It'll say first curve, we only have two curves, so you hit enter. Second curve is my red y2, enter. Guess, hit enter. So you hit enter 3 times, and there's my point of intersection. So based on this data, guys, what is the year in which these two populations will be the same? And in order to answer that, we look down here at my x value of 136. I'm going to round that to 137. So if they intersect with, it was about 26 million was the output value at x equals 137, that is the year 2037. And that's the answer to the question, when will these two cities have the same population? And I predicted that using 2 linear models. All right, there's a couple definitions I'm going to go through here. These last few examples, we're going to do them algebraically. When we classify a system of 2 linear equations, consistent systems have at least one solution. Among the consistent systems, we'll have two other types, independent and dependent. Independent systems have one solution, exactly one, and dependent systems have infinitely many. Okay? I've got a chart because I think that these definitions are best put up graphically. Graphical solutions of linear systems. All right, here are two intersecting lines. You can see I've got blue, I've got red, and they intersect once. This is a line with different slope and a different y-intercept. In this case, two different lines like this will always intersect once, which is why this says one solution, which means they're consistent systems, and they're independent from one another because they're different, but they have one solution. If you have two lines with the same slope and the same y-intercept, they're the same line. If you graph both of them up, they'll be overlapping with one another, which is why we have this big purple line here. You'll have infinitely many solutions. And these are consistent, but they're dependent because they're not different from one another. All of the points along that line, that infinitely long line, are solutions. Lastly, we have this here. If you have two parallel lines with the same slope, but you've got different y-intercepts, you have two separated parallel lines with the same slope, but different y-intercepts here, they will never intersect. So we say that they have no solution, or rather, they are inconsistent with one another. And what I'm going to do lastly here in this video is there are a couple problems here. We're not actually going to solve these. I'm not going to find what points are the solutions, but look at the directions here for each one of these. Using only algebra, determine whether the following system is independent, dependent, or inconsistent. So, my y1, I'll label this as y1. 4y1 minus 2x is equal to 6. I'm going to get y by itself in each of these, so I'm not going to maybe talk through this at length here, but let's get y by itself. Sorry, that's not a 6x there, that's just a 6. Okay, yes, I am just double checking. 6 divided by 4 is 3 over 2. So that's 1/2 x plus 3 over 2. Let's do this for y2 now. If I just divide both sides by 8 there, you can see I'll get 1/2 x minus, once again, 3 over 2. Now, these have same slope. They have different y-intercepts. If they have the same slope, but they have different y-intercepts, these are like two parallel lines which never cross. These are inconsistent. So let's go through. I'm going to do these last couple examples, and I might do them a little quickly. All right, I'm going to take this first one, y1, and then y2. If I add 3x to both sides, y1 is equal to 3x plus 4, and we're good. Let's do negative 1/3 y2 is equal to negative x plus 1. Multiply both sides by negative 3 here. 3x minus 3. I have the same thing going on here. Same slope, different y-intercepts. So these are inconsistent. Let's try the last two. Okay, these have different slopes, different m, and different y-intercept, a different b I'll just write. These are two different lines. Two different lines like this will always intersect one time, exactly one time. So these are independent lines, all right, but that they are consistent because they do have a solution, and independent. You try the last one on yourself, as long as this video doesn't get too long for Edpuzzle. What do you think? Pause the video. Try to do example 7 on your own and determine are they inconsistent, independent, or dependent. If you did pause the video and you got dependent, good work. If I take this as y1 and y2 and I solve for y, I end up with y1 is equal to 2x minus 3 and y2 is equal to 2x minus 3. These are in effect, like I said, the same line. Same slope and same y-intercept, or like I said, overlapping. So these are consistent and dependent. So there we have it.